号码，我那叶子疫苗考就考，那没考，有一层有，有一层有，有一层是自动爆掉的。那自动爆掉哦，你这么好奇？他说他自己，看一下，真假？媒体出太难。有点痛。我应该把那个2拿掉啊，应该出原本那个。对吧？确实。因为其实我同学在算的时候，也都不会有那个。我实做他也不会有那个。那个只是我单纯觉得题目要难一点点。是，不要跟枪一样，干没有题目爆掉，好像有这些。应该不是打错分数。找他在又一个页，哦，看到，又一个页面比我还多呢。蛮惨。很抱歉。你感受不到你的抱歉。这平均有67，我应该还好。应该好像有部分是我觉得已经到一个失误的问题。操！不是你那题加上就有77，那你加上就应该就有77到80。没有。我那他没有啊，那题我才15分，他40几85分，你加上70、80。没有，我说平均。我不能送分啊。
Okay, everyone, let's start teaching. Okay, so this time we start talking about Laplace transform, and well, there is a Laplace transform equation, but instead of equation, we see that there is a very important concept for Laplace transform that was not in Fourier transform. That's this concept of region of convergence, which we abbreviate as ROC. Okay. So ROC is a concept that we don't have in Fourier transform, because in Fourier transform, the convergence we say is either this function is Fourier transform converge or not. It's converge or not for every t and every omega. But for Laplace transform, we have this more detailed analysis for convergence. We say Laplace transform, you transform some time domain signal to frequency domain signal. But now we have this weird complex value frequency S. Okay, so S is like a complex value frequency, and we see that Laplace transform, it will be convergent on only part of the S plane. So S is a complex value, so it has a real part and an imaginary part. And we see that a lot of times Laplace transform only converge on part of S, and we think this is okay thing. And in fact, we even we find out that this region of convergence is even an important part of the Laplace transform, as we see in this example, this pair of examples. So in example 9.1, we have our familiar this one-sided exponential decay function, and we see that it Laplace transform to 1 over s plus a, with but only convergent on the number of on those s, such that the real part of s is greater than minus a. So this shaded region here. But we see that there is another function x of t that looks kind of like this, but totally different. It's this minus e to the minus at u of minus t. So this is an exponential function where only has value on t less than 0. And we found out that if we do the integration, the algebraic part is totally the same as this thing. So the algebraic part is still 1 over s plus a, but it has a different this function in the frequency domain, it has a different region of convergence. It's region of convergence. So you do the Laplace transform integration, you see that this integration only converge on those a's such that the real part of S is less than minus A, where A is A here. Okay, so you see that we have two very different type of main function. They Laplace transform to this same 1 raised plus A expression, and the only way to tell them apart is that they have a different region of convergence. One of them has a region of convergence, i.e. s greater than minus A, and the other one is a region of convergence, i.e. s less than minus A. Okay? And so if you want our Laplace transform to have a one-to-one correspondence between its time domain signal and the frequency domain signal, then we need to specify the region of convergence to know that the time domain signal is this x of t or this x of t. This x of t that only has value when t is greater than 0, or this xt only has value for t less than 0. Okay, and yeah, so this is a reminder again that we will talk a lot about ROC, and ROC is an important part of Laplace transform. Okay, and then let's jump to, let's see, then we start talking about properties of ROC, and then the first property we see is that the ROC are considerable strips, and some S is an ROC as long if only if if the sigma is a real part of S, then we want the x of t times e to the minus sigma t to be absolutely integrable. So so this equation need to satisfy for your signal. Then we think this vertical line on sigma is inside ROC. Okay, so ROC will be considered strips, and we see that ROC actually is even simpler. ROC can only be one strip at most. Okay, so ROC can be at most one strip, and but this strip can extend to plus infinity or negative infinity on the left hand side or right hand side, and or you can extend to both sides, and it will be the whole plane. And we're seeing some properties, so we see that if our signal is a finite duration signal, then the ROC will be the entire S plane. And we see that if our signal is right-sided, so signal is sketched like this, then our ROC will also be kind of right-sided. It will extend to right infinity. And if the signal is left-sided, then ROC will extend to left infinity. And if ROC is whatever, then if the signal is whatever, then ROC can be at most one strip. Okay, so those are ROC, and we also see some very easy properties with respect to poles. So obviously ROC cannot contain poles because poles are divergent, and also for rational functions, the ROC will be bounded by poles. And we'll spend a lot of time studying rational function for Laplace transform. Okay, and so that's a quick review of what we covered this time. Any questions so far? If not, then we'll go to what you might expect. So we have talked about the Laplace transform integration, and now we want to talk about the inverse Laplace transform. Okay, and there are two ways to do inverse Laplace transform. That's kind of different from what we're doing. I guess it's a bit similar to Fourier transform, but we are having different organization. Okay, so first method is there is another integration that you do. You can to do inverse Laplace transform, and but then we'll talk about for rational function. So here the important part is the rational function. We can do inverse Laplace transform by just doing partial fraction expansion and use the non-Laplace transform pair to do the inversion, kind of like what we do when we use Fourier transform to solve the differential equations. Okay, so those are two methods that we'll be talking about today. And so let's first look at the integration. And the integration, we basically use, we can derive the integration by using Fourier transform. because we know how to do inverse Fourier transform, and we know Laplace transform is Laplace transform on some sigma is Fourier transform of x of t to the minus sigma t. Okay, so we say the big X of sigma plus j omega is the Fourier transform of x of t e to the minus sigma t. Okay, and so from this, then we can inverse Fourier transform these things, both things. Then if we inverse Fourier transform this big X of sigma plus j omega, then we will get back our x of t e to the minus sigma t. Okay. So this we know how to do. We apply the inverse Fourier transform formula. So we fix the sigma here, and basically we inverse Fourier transform with respect to omega. So we have this inverse Fourier transform integration 1/2 pi integration of your function times e to the j omega t then d omega. So our integration on omega. Okay. And from here, then we have closed form expression for how to get your x of t from big X of x, big X. Okay, so x of t, so you just put this e to the sigma t to the other side, so you multiply e to the sigma t on both sides. Then we have this equation. This is how you get x of t if you want to do integration big X to go back to your x of t. So your x of t is this integration 1/2 pi 1/2 pi and integration on omega from minus infinity to plus infinity, then big X of sigma plus j omega e to the sigma plus j omega td. And as we said, the integration is omega. And this is a well-defined equation. Okay, and so you have this omega integration on real value minus infinity to plus infinity, and you can do this. Okay, and I guess this integration okay, I guess we'll talk about this later. Yeah, I'll talk about this now. Okay, and so this is the integration on omega, and but then if you want to use this, then there is a question. So we have this here. Once again, so let's change the teaching here a little bit. Okay, so we have this equation here. This is omega. Then there is a question of what sigma you want to pick, right? So there is this sigma is not integrated over. This sigma is something you pick. Okay, and what sigma you pick is, if you jump ahead a little bit, is you cannot just pick whatever sigma for this to work. So what you pick is you want the sigma to be inside ROC. Okay, so sigma should be inside ROC, and so it will be some integration like this. So you have, say, your ROC is this strategy region, then you pick whatever sigma inside ROC, and then you will integrate omega from negative infinity to plus infinity. So kind of integration along this line, and whatever sigma you pick will give you the same result. Okay, and so that's the integration you can do, and we can make this a bit more formal. So you see we have both sigma plus j omega here, and we can say we know sigma plus j omega is this complex variable s, and we can change this integration from this real variable omega to this complex variable s equal to sigma plus j omega. So so we have x of s, and this is e to the s, and ds. Okay, and but now we do a bit of a weird change of variable. So s was sigma plus j omega, and we only change omega. So if we do this differential analysis, then we know ds equal to jd omega. So the d omega was 1/j ds. So we get 1 extra 1/j from changing d omega to ds. Okay, and but now this is something that you might not learn in, you probably didn't learn in your freshman calculus. So this is now we go from just conventional integration to complex analysis. So now we are doing integration over a complex number, and because complex number don't lie in a line, so we know complex number actually is in a plane. So we need to specify the pace of the integration on your complex plane. So the pace of your integration was what do we say? So it was sigma minus j infinity to sigma plus j infinity. So correspond to this line. So say this point is sigma. So say we have some point sigma here, and so we are integration on a line. Okay, and now okay, so this is called the contour of integration. So so if you go to complex analysis class, you will learn about this contour integration, which we will not go into detail, but we'll talk about a bit of its property. Okay, so contour integration is a straight line. So it's a line on the complex plane, and it's this thing from sigma minus j infinity to sigma plus j infinity. So this is a straight line here. Okay, so you need to do this contour integration. Okay, and as we said, this contour integration, you cannot choose whatever sigma. Okay, so you need to choose sigma inside your ROC, because your big X is only defined inside ROC, and if you do so, you will get the correct answer. And and as we say, we can also pick any sigma. So we can pick this line or any parallel line inside the ROC, and that will give you the same result. This is something that you can get from a property of complex analysis. Okay, and so there is a property about contour integral says that if you do a contour integral over a circle, because you are now you are actually integrating on a complex plane. So you can integration over a circle, then if the circle it has no poles inside, then this contour integration will actually give you 0. And that also means if you have two different contours, so you have a contour 1 and a contour 2, and in the middle part so this region that enclosed by contour 1 and contour 2, if we don't contain any pole, then because the integration of circle is 0, so it's like this part is the reverse of the other part of the circle. So this integration and this C1 integration and this C2 integration will give you the same integrated result. And this is why, and this can be used to explain why we can pick whatever sigma inside ROC to do the integration. Because we know there is no poles inside ROC, so you have this sigma 1 parallel line. Then you can think about there is a sigma 2 parallel line. Then they kind of so you can kind of connect them together at the plus infinity and the minus infinity, and then you see that this integration and this integration, if you connect them to plus minus infinity, they form a circle, then so that this contour integral and this contour integral they form a circle that contains no poles inside, so they will have the same integrated value. Okay, and yeah, and there are more ways to do this formal tricks and theorems to do the formal evaluation of the contour integral, but this is something that we don't talk about in this class. Okay. So you can study more in complex analysis to know how to do contour integral. I guess if you want to do straight up integral, you can use this formula. But this is not what we will do most in this chapter. What we will do mostly is actually we will do, okay, so this is a contour integral we can do. But we will actually mostly do inverse Laplace transform on rational functions. Okay, and so if you do the inverse Laplace transform on rational functions, then we can use partial fraction expansion, and the example we already solved. so these Laplace transform pairs to just basically look up table and do inverse Laplace transform. Okay. So that's a lot like what we do in chapter 4 to inverse Fourier transform to rational functions of j omega. Okay. And so let's see some example. But because of Laplace transform, there is a carry for ROC. This will be more complicated than what we do in chapter 4. Okay. So let's see these three examples. So assume we already do our partial fraction expansion. So we have rational big X of S, and assuming there is no multiple order poles, we can do partial fraction expansion of it into this linear combination of some coefficients over S plus AI. Okay, so we have those partial fraction terms of 1 over S plus AI, and and then we need to look at then we want to do inverse Laplace transform for this. To do inverse Laplace transform for this, and what we do is what we start today. So we use these two examples. So we have we know that 1 over S plus A inverse Laplace transform to either e to the minus ATU of t or minus e to the minus ATU of minus t. And then here comes to our careful analysis of the ROC. So if the ROC is is to the right side of this pole A, then we know you should inverse Laplace transform to this. And if ROC is to the left side of this pole minus A, then we know you should inverse Laplace transform to this function. Okay, so ROC to the left side, you should transform to this left-sided function, and ROC to the right side, you should inverse Laplace transform to this right-sided function. Okay. And yeah, so now we have a lot of those terms with different poles and minus AI. Then we need to look at whether ROC is to the right side of this pole AI minus AI or to the left of this pole minus AI. And if ROC is to the right, then we inverse Laplace transform to this right-sided function e to the minus AI t u of t. And if ROC is to the left side, then we inverse Laplace transform to this left-sided function e to the minus at u of minus t. Okay, and so let's see this in a very simple concrete example. So let's say we have our Laplace transform is x of s equal to 1 over s plus 1 and s plus 2. So and we pick the ROC to be s greater than minus 1. So I guess I should draw a picture. Okay, so there is a picture. So the function looks like kind of this. So it has a pole at minus 1 and a pole at minus 2. And the ROC is to the right side of minus 1. Okay, and as we say, so yeah, so here we have a minus 1 pole and a minus 2 pole. Okay. And as we said, to get our this rational function on S, and to get the Laplace transform, we do partial fraction expansion. Okay? And it should be some A over S plus 1 plus B over S plus 2. Okay? And here we skip over the partial fraction expansion calculation. Hopefully you guys are already very familiar with it. Okay? So with whatever way you do partial fraction expansion, then you determine that A equal to 1 and B equal to minus 1. Okay? And so x of s equal to 1 over s plus 1 minus 1 over s plus 2. And so the first term corresponds to a term with a pole on minus 1, and the second term corresponds to a term with a pole on minus 2. And now we need to look at whether ROC is to the right side of minus 1 and whether ROC is to the right side of minus 2. And we see that, well, indeed, the ROC is to the right side of both of those poles. And so for both of those terms, we should inverse the Laplace transform to the right-sided function. Okay. Okay. And yeah, and sorry, Yeah, so the RC is to the right side of both of those poles. So we determined that we should inverse Laplace transform both of them to the right side function, and so this is the result. So we think the RC for this thing should be the greater than -1, and the RC of this thing was greater than -1, and we extended it to this greater than -2. And so both of them inverse Laplace transform to this right function e to the -at u of t, e to the -at u of t, and a was 1 here, and a was 2 here. And then we combine them back, we see that our inverse Laplace transform was e to the -t minus e to the -2t u of t. Okay, and yeah. And so frequency moment is this, and so time domain was this. Okay, this is an example of inverse Laplace transform. Is it clear? So yeah, so basically we partial fraction expansion our our rational domain big X, and for each term, it has a pole, and so we look at the total ROC, and we want to then we look at the total ROC, and we try to determine whether it is to the right of each pole. And in this equation, we see that it's right of both poles. So so we know this ROC was obtained by having an intersection of both this ROC and this ROC. Both of those ROC was to the right side of this pole, and we inverse Laplace transform to those two right-sided functions. Okay, and so we can do this example very similarly, and with different ROC. Okay, and so we have the same algebraic expression here. So big X of S equal to 1 over S plus 1 times S plus 2. But now we have the ROC to be less than -2, and we don't have a picture here, but the idea, okay, so the picture is kind of this, so we still have the pole at the -1 and the -2, but ROC is now to the left side of both poles, and we do partial fraction expansion, we still have this 1 over S plus 1 term and the 1 over S plus 2 term, but now because the ROC is to the left of both poles, so we do inverse Laplace transform, so both those partial fraction has corresponding ROC to the left, and so they will have inverse Laplace transform of the left-sided function. So this was e to the -8 minus e to the -at u of -t, and with a equal to 1 and a equal to -2. And so we combine those two terms, then we get our inverse Laplace transform here. So it's minus e to the -t plus e to the -2t u of -t. Okay, and so finally we can have another inverse Laplace transform, or another ROC. So we have 2 poles, and there was 3 possible ROC, as we said at the end of last time. So this rational function has these 2 poles, so the ROC can be to the right, to the left, or to the middle. And our last example was the case where ROC is in the middle. So ROC is between -2 and -1, so kind of like this. Then this example is a bit more complicated. So we see that for the first pole, for the pole at -1, the ROC was to its left, and for the pole at -2, the ROC was to its right. So this 1 over S -1 pole inverse transform to the left-sided function. This e to the -e to the -t u of -t, and this 1 over S plus 2 function transform to the right-sided function. This e to the -2t u of t, and so this is the inverse Laplace transform of this big X of S for ROC between -2 and -1. Okay, and so I guess this can jump back a little bit back, like here. So less time, so this is corresponding to our 3 possible ROC analysis. So we see that we said for this function we can have we have 2 poles. This is a rational function with 2 poles, but and we know the ROC of rational function must be bounded by poles, and you can have these 3 possible ROC and correspond to these 3 combination of how you invert your partial fraction expansion. Okay, so you have both of them right-sided, both of them left-sided, and one of them left-sided and one of them right-sided. And so if you just go through the all possible combination of left and right for these 2 fractions, then you see there is a fourth combination. There is a combination where you want to be the right-sided of -1 and the left-sided of -2. And but we see that this thing don't have a corresponding ROC, and indeed that's because this function is very divergent, and it don't have a convergent. And when you try to do Laplace transform it don't converge anywhere. Okay. So that's because the ROC of right to the -1 and the ROC of left to the -2 don't have an intersection. So this thing don't converge anywhere on its plane. Okay, so we have those 4 possible combination, and only 3 of them has a meaningful ROC, and they correspond to these 1, 2, 3 different ROC. Okay, and you can probably guess that when you have a more complicated example, then you have more poles on your S-plane, and then you look at where your ROC, you look at your ROC is between which poles, and then you can determine that whether each partial fraction should transform to the left-sided function or transform to the right-sided function. Okay, so that's the idea for partial fraction expansion and inverse Laplace transform of rational function. And then we have a bit of a supplement here. So this was something we talked a little bit about, but don't go into too much detail in chapter 4. So this is what happens when our rational function has more order on numerator than denominator. If the upper polynomial has more degree than the lower polynomial, then you cannot do partial fraction expansion. And in that case, what we do is we basically do the division first. So we divide, we try to do long division between the upper polynomial and the lower polynomial first. So we will have this quotient term, that's just another polynomial. So basically the first 2 terms here is a polynomial. And then the rest of the term will have so we have the quotient term and the remainder term, and the remainder term will have the numerator having less order, having smaller order than the denominator, and then we can do partial fraction expansion on the remainder term. Okay, and so what about the? Okay, so basically we have if our big X is some numerator divided by denominator, then we can write n equal to q plus some remainder times d, something like this. And so then we do the partial fraction expansion on remainder. Yeah. Oh, sorry, I write this wrong. Should be q times d. Should be q times d plus the remainder. This is the multiplication thing. Okay, and anyway, and if you do this, then you see the remainder term. You can do partial fraction expansion. Then you can ask, how do you do inverse Laplace transform on this polynomial? And the answer is you look up other formula. And here we give you the Laplace transform of a polynomial. Okay, and so first is the constant term. the constant term, I think we already do this Laplace transform pair. So constant will just inverse Laplace transform to delta function. Because you do Laplace transform delta function, then it's very easy to see that the integration is just 1 and the conversion everywhere. And for higher order terms, so those s to the q's power, then it's actually, so here we just call later we'll see this derived by properties, but they actually correspond to differentiation on delta function. So if it's nth order term, nth order on s, then it's a u sub n function, that's the nth derivative on delta function. And the small reminder, we have talked about those singularity functions. So those nth order derivative, they are those doublet, triplet, etc. functions. And there's the singularity function, they have this weird property that if you convolute some function with those case order singularity function, then you get a case order derivative on your signal XOT. Okay, so that's a bit of digression. Any question? And that's how to deal with higher order n over s here. Okay, and so here we finish how to do. I guess partially finished because we only deal with the case where we don't have multiple poles. But as you might imagine, then if we have higher order poles, then you will need to use the differentiation formula to derive the inverse Laplace transform pair. Okay, just like in chapter 4. Okay, so then this is how we do inverse Laplace transform for rational function. You first do partial fraction expansion, and then you need to look at your ROC to determine where you want to have the left-sided inverse Laplace transform or the right-sided inverse Laplace transform for each partial fraction. And once you determine where it's left and right, you just look up the table and write down all the inverse Laplace transform for each partial fraction, and then just to have a linear combination of all the inverted partial fractions. Okay, and so that's the inverse Laplace transform for rational function. And in the remaining 50 minutes, let's talk about something basically just concept-wise, but it's an interesting concept we can have from our Laplace transform expression. Okay, so we actually go back to Fourier transform. So we say Laplace transform is a generalization of Fourier transform. Fourier transform was only transformed to this J omega axis, and the Laplace transform is transformed to the whole S-plane, and it has all those poles and the zeros on S-plane. And then we can from the Laplace transform we can actually go back and get some properties on Fourier transform. Okay, so this analysis we mostly do on rational Laplace transform. Okay, so when our big S over S is a rational function, then as we say, because it's a polynomial divided by another polynomial, and then we can factor both polynomials and having the roots of those upper polynomial as beta I and the roots of the lower polynomial as alpha j. Okay, excuse me. Yeah, so for any rational Laplace transform, we can write it as this. And as we say, we can mark those poles, and so we can mark those zeros on your complex plane and then mark those poles on your complex plane. Okay. And then we can have some geometric interpretation of this value. Okay. So we look at this formula and we think about from here what will be the Fourier transform of this function b. So Fourier transform will be this big X taking value on this j omega axis. Okay. And so what's this value on those j omega axis? Then we see that we have product of so we think about what's S value of this, then that's product of S value of all those terms divided by product of S value of all those terms. Okay, and then then we think about what is S minus some A. Then it's actually the length of so S minus A as a complex value is actually this vector from this point A to your point A. Okay. And yeah, so this vector S minus, so this complex value S minus A can be think of as this vector from A to S. And then you take the absolute value, then the absolute value of this complex number is the length of this vector. Okay. And so if you think S minus A as that way, then you see that here we have the product of a whole bunch of vectors from the zeros of your Laplace transform divided by the length of these vectors from your point from those poles of your Laplace transform to your point. Okay, and also so that's the length, and then you can also read the angle here. So this vector also, so if you think about the complex number, then it has a length and it has an angle. Then this angle theta is actually this angle theta here. Is the angle of this vector on complex plane. Okay, and yeah, so that's the geometric interpretation of this thing. So I guess it's easier to see an example of how this can give us some qualitative analysis of our Fourier transform. So let's say we have our very familiar function 1 over s plus a. Okay, so we have 1 over s plus a, and then we want it to have a Fourier transform, so we pick the usual convergence like this, so that the ROC contains the purely imaginary line. Okay, and yeah, so our Fourier transform will be this 1 over j omega plus 1 over 2. And now we go to our pole zero plot. Then we see that we have a pole at minus 1 over 2, and the ROC was greater than minus 1 over 2. So our geometric axis, this Fourier transform axis, is inside ROC. Okay. And from here, then we can read basically how this thing will change in magnitude with respect to omega. So it's so this vector of j omega plus 1 over 2 is a vector from minus 1 over 2 to this j omega point on your imaginary axis. And then you see that the length of this vector is shortest when your omega is 0. So it's here, and when your omega go to plus infinity and minus infinity, the length of vector gets smaller. So you see that your big X of j omega is largest when omega is around 0, and gets smaller when omega goes to plus infinity and negative infinity, because it's 1 over the length square of 1 over the length of this vector, and also the angle of your big X can be read from this plot here. You see that the angle should be 0 when omega equals 0, and the angle should go to pi over 2 when omega go to infinity, and the angle should go to minus pi over 2 when omega go to minus infinity. Okay, so that's a bit of analysis, and basically, I guess on the very high level, you see that when your omega is near some poles, then your big X of j omega will have a larger magnitude. So here you see when you change your omega, and when it's near this minus 1 over 2 pole, then your big X of j omega gets larger. Okay, and from here we see that we can design some interesting system that's called the Opitz system. Okay. And Opitz system is a system that has a very symmetric distribution between its poles and 0. So it's a system where when rate has a pole at I guess whenever it has a point at minus a, it has 0 at plus a. Okay. And so maybe it has another pole here, and it has a 0 here, another pole here, and it has a 0 here. Okay, and then and then we can write our big X of S. Then you see that big X of S is something like this: is some constant times S minus a over S plus a. Okay. And so its magnitude will be this big N. So its magnitude on this j omega axis will be this big N, and then its magnitude of S minus a divided by magnitude of S plus a. Okay, and then here comes y is O plus. Then you see this system for every omega. Then this S minus a will have same magnitude as S plus a, because you can just see from geometry here. So this omega is distance to a is always equal to its S distance to minus a, just because this triangle has equal distance here and here. Okay, so whatever omega you have, the magnitude of big S of S is the same. And so that's why the system is called open system, because the magnitude of frequency response is constant. Okay, because it always has equal length to a pole and a 0. Okay, and yeah, so that's why it's called the open system, because the magnitude of this big H of j omega will be always a constant, but they can have a different angle. You can have a different angle when you change omega. So some phase on your big H of j omega, because the angle will be this theta 1 this theta 1 subtracted with the theta 2, and it will change when you change omega. Here is an example of open system with just 1 0 and 1 pole, and it has this weird change, and it has this change of angle. And the change of angle looks a little weird because the angle has some symmetry around 2 pi, and so this pi is actually same as this minus pi. So you can think of this as angle from 0 to minus 2 pi when you change omega from minus infinity to plus infinity. Okay. And yeah, so I guess that's all we want to talk about today. Then we can have a bit of a small review of what I talked about today. And so we start with remind you again that RC is a very important part of Laplace transform. And indeed, we see that today we talk about inverse Laplace transform of a rational function, and we see that indeed we need to use RC to determine our inverse Laplace transform. Okay? So for inverse Laplace transform of rational function, first we want to write in partial fraction expansion, those partial fractions, and has those roots and different AI, and then we need to look at RC, just like in this example. We need to look at the RC of a total function and determine whether the RC is to the left or right of each individual pole. And if RC is to the right of this pole, then the partial fraction then that partial fraction should inverse the Laplace transform to a right-sided function. And then we see that if the RC is to the left-sided of that pole, then you should inverse the Laplace transform to a left-sided function. Okay. And so that's the inverse Laplace transform for rational function. And we also have a formula that's inverse Laplace transform for general function. And usually it's pretty hard to do. It's pretty hard to do integration. And but here you need to remember that you need to pick a sigma that's inside RC. And for whatever sigma inside RC will give you the same value. Okay. It's an integration you can do, but it's quite complicated, and we will mostly avoid, and we will do inverse Laplace transform on mostly rational functions. And also we see that this pole and zero analysis can give us some intuition on our magnitude of and the angle of our Fourier transform, because we know Fourier transform is Fourier transform is a Laplace transform on this j omega axis, and on a rational function, rational function, then we can think about how this j omega point is how far away is it from each point 0, and because we know for rational function, the Laplace transform is can be expressed as this distance to the zeros divided by the distance to the poles. So so you can just think about how your j omega is how far away is it from each 0, and how far away is it from each pole, and you can get a qualitative estimate of its magnitude. Okay, so for example, for this opaque system, you have each pole and the 0 is paired up. Then you know that. So for example, this 1 0 and 1 pole opaque system. Then you know that for whatever j omega you choose, this j omega has the same distance to this 0 as it has as to its distance to this pole. So when you write this s minus a over s plus a, then the magnitude is always 1 here, because this length is always same as this length, and so this will give you an opaque system such that the absolute value of h over j omega, big H over j omega, will always be 1. Okay, and so that's finish what I want to talk about today. And next Monday we'll start to talk about the properties of Laplace transform. And once again, for all the properties, we now need to think about how those properties affect the ROC of your Laplace transform. Okay, so see you next Monday.
Yeah. 这个礼拜题目要出一个新的。